Okay, today we're going to multiply some radical expressions. You simplified individual radicals one at a time, but now we're going to put two of them together, or even three of them together. You can put multiples together, and then simplify them from there. So here's our multiplying rule. If you're multiplying radical expressions, a times square root of x times b times square root of y, well, there's a multiplication in here, it's implied. There's a multiplication right here, it's implied. So we're going to use our commutative and associative properties to just rearrange and regroup these. Put the coefficients together and you get a times b, and then put the two radicands together. You get x times y. Notice they stay inside the radical. So all you're doing is multiplying the coefficients and then multiplying the numbers inside the radicals. Sounds simple, but there's a couple of little tricks as you go along. Because once you multiply, you have to simplify what you have new. Well, that means that if you have big numbers inside these radicals, you may end up with a huge number in there that you don't know how to deal with. So before you multiply these radicands, always try to simplify them first individually. That'll keep your numbers as low as possible. If you can break down one of these square roots into a smaller number, that means you're going to have a smaller product when you start putting it together. So simplify before you multiply if you can. Sometimes neither of these are going to have perfect square factors, and you can't simplify either of them. But just by factoring them, if you can find a common factor, here's a common factor between those two radicals, when you multiply them together, they're going to make a perfect square. So even if you can't get it to simplify by taking out a perfect square, breaking it down to factors to find a common factor might help you out when the numbers are bigger. All right, so let's take a look at a few. Before we actually multiply them, there's just a quick little rule, which is kind of going to be the easiest question you're going to see. And here you go. The square root of 3 squared. Well, square root of 3 squared means the square root of 3 times itself. Square root of 3 times the square root of 3. And now I'll multiply what's inside the radicals, the two radicand numbers, which will give me the square root of 9. And the square root of 9 is a perfect square, it's just 3. Well, take a look at the original problem. Where's 3 inside? My final answer is 3. And that's because the square and the radical square root are inverse operations. So they just do and then undo each other, which means you don't actually have to work this out. Anytime you square a square root, your answer is just the radicand. So the square of the square root of 7 is just 7. The square of the square root of 3w to the 5th x is just 3w to the 5th times x. Squaring a square root just eliminates the radical symbol because these are inverse operations, just like if you did plus 4 then minus 4, or times 6 and then divided by 6. You get back to where you started. So if you take the square root of something and then square it, you just did the reverse, the inverse, you're back to where you started. So there's a shortcut for those. That's an important rule when you're solving equations as you move forward later in math, and it's a quick and easy way to solve some of these problems. Those are basically freebies. All right, let's multiply some now. Square root of 5 times the square root of 3. Well, neither of these numbers can be simplified, so I'll just multiply them together. There's no coefficients, so it's just the square root of 15. And now I take a look and I say, can 15 be broken down into any perfect square factors? In this case, no. 15 has no perfect square factors, so that is the simplest radical form. Sometimes you can't simplify the radical because there are no perfect squares inside to factor out. That's all you gotta do for some of those. This guy, not so much. Square root of 6 times square root of 3. I'll multiply them and get square root of 18. And now 18 does have a perfect square factor, and that perfect square factor is 9. So break that 18 down into 9 times 2, the same way we just got done doing the last couple days. And now that 9 will come out and become a 3. Radical 2. All right, pretty simple to start. Let's mix it up a little bit, throw in some coefficients, and some bigger numbers too. 5 times the square root of 21 times the square root of 33. Well, no coefficient here, so I know I'm going to have a 5. Square root of, and 21 is 7 times 3. That can't break down. There's no perfect squares. 33 is 11 times 3. That doesn't break down to perfect squares. But notice both times I said 3. Because if you multiply 33 times 21, you're going to get 693. You probably don't want to try to find factors of 693 that are perfect squares. But if I take a look at this 21 and just break this down to 3 times 7, and take this 33 and make it 3 times 11, and then when I multiply these together and put them inside this radical, I have 2 3's. Well, my 3 squared makes a 9. And then a 7 and an 11, which together make a 77. And now, 9 times 77, well, guess what that is? 693. You didn't know that, but you did when you broke it down to smaller numbers. And now that 9 is a perfect square to come out. 9 comes out and becomes a 3. 3 times 5 is 15. And the 77 remains in the radical because there are no perfect square factors. That's the way I saw it. Some people, some books, some teachers like to say, well, if you have a pair of factors, it comes out as 1. If you have a pair of 3's, then 1 3 comes out. That's one way to look at it. It's not the way I look at it. I don't like doing that because it's too easy to take the wrong number out. I like to see a perfect square inside and take its square root to actually do the operation. Just my personal preference. Same thing here. 18 times 21 is 378. I don't like that at all. But let's see what I got. 18 has a perfect square factor. 18 is 9 times 2. So this is able to be broken down before I even multiply. So this 9 can come out and become a 3. So this now becomes 3 radical 2. And this is 9 radical 21. And now I'll multiply the coefficients together. 9 times 3 is 27. And 2 times 21 inside the radicals is radicand numbers. 42. 42 has no perfect square factors. It's a perfect number. It has no perfect square factors. Here's my final answer. So sometimes breaking these numbers down ahead of time makes the second step a whole lot easier because numbers are more workable. They're smaller. They're more comfortable numbers. Now let's throw in some variables too. Go for the whole gusto here. 165, that's a big number. I don't think there's any perfect square factors now. Let's see, 165 divided by 5 is 33. That's not going to help me. But I'm going to just say 165 divided by, look at this number, 15. There's a 15 here. I might want to try to match up this 15 with that. So if I do 165 divided by 15, that's 11. So this 165 is really 15 times 11. And this is a 15. And those 15s are going to pair up to make a perfect square. So let's do some procedural stuff here. Let's multiply the coefficients. 9 times 7 is 63. Then inside my radical, let's see, I've got 2 15s, which makes a 225. And an 11, which is going to be my not perfect square that remains inside. And then I'll put together my variables, P, R, Q, let's see, so that's just a single P. I'm going to alphabetize them. A Q to the 4th and R to the 4th. If you wanted to, you could have taken these perfect square variables out in the beginning. I don't bother with them because working with the exponents is just divided by 2. It's not like it gets that much harder. But sometimes these numbers, so like if I was to multiply 165 times 15, have that product, which is, give me a second, 2475, not a comfortable number to work with. But by breaking that down, I can do that in pieces much easier. Variables and exponents, remember, you're just dividing by 2. It's no big deal. So now let's take all of our perfect squares out. 225 comes out as a 15. So the 63 that's there times 15 gives me 945. The P stays because it's a first power. The Q has an even exponent. Bring it out. Divide the exponent by 2 and you get Q squared. The R's got an even exponent. Bring it out. Divide it by 2 and you get R squared. And left inside the radical is the 11 and the P. You may have heard me pressing some calculator buttons. I absolutely expect you to use a calculator to do some of this multiplication. There's no reason to multiply some of these numbers by hand. But it's about the procedure of recognizing the perfect squares. It's not about the computation sometimes. It's about recognizing the perfect squares and knowing how to simplify them, even when the numbers are large. All right, last but not least, let's see. 5k to the fourth. 5 doesn't break down. I'm not going to bother with this k to the fourth because, like I said, the exponent should come pretty easy. 490, big number, but that's 49 times 10. And 49 is that perfect square. So before I multiply these, I'm going to take that 49 out. So I'm going to rewrite this as 2 times the square root of 5k to the fourth. That's a really bad k, sorry about that. Times 49 comes out and becomes 7 times the square root of 10k to the fourth. All right, now I'll put them together. Multiply the coefficients. 2 times 7 is 14. Inside the radical, 5 times 10 is 50. And k to the fourth times k to the fourth, that's k to the 8th power. Now let's break this down. 50 breaks down into 25 times 2. All right. And then the 25 is going to come out and become a 5, because that's a perfect square. The 14 that's already there multiplies the 5 and becomes 70. The k to the 8th comes out because it's an even exponent, perfect square, divided by 2. K to the 4th. And inside the radical, the only thing left is the 2. Requires a lot of number sense, requires some computational skills, requires some critical thinking as you go along. But it's really just a combination of everything we've done in the last 2 lessons, just with some larger numbers and the multiplication in between. All right, have fun.